So we have a manufacturer cutting squares from the corners of a rectangular sheet of metal measuring 3 centimeters by 8 centimeters. So as always, you want to start with a diagram. So we have this rectangular sheet of metal. The long side is 8 centimeters long, and the short side is 3 centimeters long. And then the manufacturer is cutting squares from each of the corners. So my little squares, these are the squares that are actually being cut out of the metal. And they're all the same size and shape of square. So it says, let's let x represent the side lengths of the squares, and we want to find the value of x that will maximize the volume. In other words, we want to know how large should these little squares be that are being cut out, so we create a box that has the biggest volume possible. So if you can imagine then, basically, if these little 4 squares are gone, let me adjust my picture a little bit. When you take a look at the box here, I'm going to kind of make this dotted. This dotted region, this is going to represent the base of what the box is going to be once we fold up the 4 sides. So let me draw an adjusted diagram over here, basically. So there's my base. This is the base of my box. And then if I've gotten rid of those little 4 corners, then I have basically these 4 flaps, if you will, that are going to get folded upward to create the sides of the box. So this is what the box would look like if you had it open, laid out flat. Okay, and then these 4 sides here, this one, second and third and fourth, these are the flaps that would be folded upward to create the sides. So we know that the volume of a rectangular box of this shape is going to be length times width times height. So we just need to figure out the 3 dimensions. What's the length, what's the width, and what's the height of this new box. So again, going back to my original diagram, if we're looking at the base, let's look at the length here of the new base of my box. So the piece of metal had a length of 8, but the base of the new box is not going to be length 8 because we've removed a little square here of length x and a second square over here of length x. So essentially we've removed 2 x's. Think of it as 8 centimeters minus 1x minus another x. And that's going to leave me with 8 minus 2x. So this new length will be 8 minus 2x. Over on this diagram, it would be like this, 8 minus 2x for the length of the base. Now let's look at the width. Once again, it used to be 3. So now we're looking for this width here of the base. It used to be 3, but we took away a length of x for this square and another length of x for the second square. So now I'm going to have a length of 3 minus 2x. 3 minus 2x, that's going to be the second dimension for the base, 3 minus 2x. So we have basically the length and the width in my volume formula. So now I'm left to find the height. And it might be helpful to look at this with one more diagram, more of a 3-dimensional diagram of what this box would look like once we actually fold up the 4 flaps. So we're going to end up with a rectangular box, something that looks like that. If I label, we know we have a base here that has length of 8 minus 2x and a width of 3 minus 2x. So now our question mark here is what's the height of the box? But if you take a look at our diagram, all these little tiny flaps that we're going to be folding up, these lengths here are x that I'm labeling. So if you can imagine, when I take those flaps and fold them up, then the height of the box is also going to have a length of x. The height would be x as well. So now we have the 3 dimensions of our box. So we can write our model for volume. So the volume, which is what we're trying to maximize, was length times width times height, and we've found the new dimensions to be 8 minus 2x for the length, 3 minus 2x for the width, and then x for the height. So this is our volume model. Now, the goal in the problem, the goal was to maximize volume. So this is certainly going to be a problem that we can take to our graphing calculator to help us compute the maximum. Now, if you wanted to distribute and simplify this volume function, you could. But because the question doesn't require that of us, since we simply want to go to our graphing calculator to generate a graph, I would recommend just leaving the volume model in this form. This would be factored form. So let's go ahead and graph it. So at this point, you might want to pause the video, get your graphing calculator, see if you can graph this model and come up with a decent window. Keeping in mind that if we had multiplied this whole function out, we would have x times negative 2x times another negative 2x. That would be positive 4x squared. So that's a 4x cubed. So that's a cubic. So we're going into this knowing the basic shape of the graph. We should have some sort of an S shape. All right, so I graphed it on my graphing calculator. And it turns out I actually didn't have to change my window at all. A nice standard viewing window seemed to work. I'm going to have an S-shaped curve that looks something like this. Just a standard viewing window from negative 10 to positive 10 in both the x-axis and y-axis. So if we're looking for the maximum volume then, we can see that we're going to have a maximum occurring right here. So this is the point that you want to compute utilizing your graphing calculator. You want to calculate the maximum. So once again, pause the video as necessary because you definitely want to check that you can do these keystrokes on your own. I did, and I'm getting a maximum of this value, approximately. The maximum is 0.666. There are more decimals than that, but I'm just jotting down the first three. And then my volume was 7.4074-ish. So this is the point that your graphing calculator gives you for the maximum. And remember, the graphing calculator always labels everything as just x and y. However, we don't want to label it as x and y. We want to pay attention to the function, which up here was my volume function. We want to pay attention to our variables in the problem. So our input variable was x, but our output variable was v. So we actually have an x value, and then we have a volume. So if it's a two-part question asking you for what was the value of x, once again, if we go back to our original picture, x was the size of the little squares that we cut out of our sheet of metal. It was the side length of a square. And if we read the problem, it's saying we want to find the value of x that maximizes the volume. So we have that value. Our side length is going to be approximately 0.666. If we round to 2 decimals, that would be 0.67. And once again, our units over here, let's see, it was 3 centimeters by 8 centimeters, so we're looking at centimeters. So 0.67 centimeters. That's the length of the little square that we're going to cut out. And then if you want to actually jot down the maximum volume that you can create, then the maximum volume would be 7.41 if we rounded 2 decimal places. And that's going to be a measurement of centimeters cubed, or cubic centimeters, will be the maximum volume for this box if we had a sheet of metal that measured 8 centimeters by 3 centimeters, and we were removing squares from each of the 4 corners.